We have this character here, and some people may recognize the character from a popular office-based comedy series. Reminding us that this is not a free body diagram. This is an illustration, okay? So if you draw a picture like this where there's like all this table involved and some boxes and stuff, this is an illustration. It's not a free body diagram. Strictly speaking, a free body diagram is free objects just floating around in the air like we had in the previous pictures. But we're going to dress this thing up because there's not really any scenario around this illustration yet. Give it a reference frame. We say, let's call it up positive, and we'll talk about to the right and to the left. Make to the right positive, to the left negative, down. And we'll say that there's an applied force. I'm even going to remove the person from this situation. We'll just say that somehow there's an F applied of 18.0 newtons. 18.0 newtons. And we'll say that the first mass is 10.0 kilograms. And you know, even though this isn't a free body diagram, it can be really helpful for a lot of people to think through their problems by labeling a diagram with your givens. So you're kind of killing two birds with one stone. You're helping yourself to visualize a scenario, but you're also listing your givens, which you have to do for communication purposes anyway. So we mass 2, 5.00 kilograms. Yep.
What's the F applied?
The F applied. Oh, you're right. You know what? That's like a dirty, messy thing. I said it out loud. It is 18.0. Oh, that's nicer. 18.0 newtons. And I think for this scenario, we're going to say that the floor is frictionless. Again, just to keep things simple for now. So we've got this frictionless floor. Before we go any further, I want to list off some promises. We will only deal with rigid systems. And I'll unpack what that means. But we will only deal with rigid systems means that we won't deal with scenarios where the boxes collapse and squish like a sponge. We won't deal with pulley scenarios where the rope is stretchy like a bungee cord. A rigid system means that the objects involved remain their constant shape. Okay? So no stretching, no collapsing. All objects, as a consequence of this, all objects within a rigid system so it's not really a new promise, but it's kind of a statement that's a consequence to the first promise. Move together with a common acceleration and have common instantaneous velocities. Okay, so that's a promise. And actually that makes a lot of things easier. In the real world, do you think that systems are ever truly rigid? No. Even pool balls compress a little bit upon impact, right? Think about like pool or billiards. Anyone who's ever seen a golf ball in slow motion, you know that it deforms. And so like this is a promise we're making in the magical world of physics. Look, magic and science, right? But this is fictitious. This is a simplification that as we go to higher levels of physics and engineering, we strip away the simplifications, okay? But for now, we're keeping this as a simplification that's a useful lie, okay? Just to unlock some of the thinking power and like the problem solving, okay? That's all it really is. So first things first, free body diagrams. I think about my two objects. We got object 1 and object 2. I even labeled them with like little circular labels there, 1 and 2. And we'll do the low-hanging fruit first. Force of gravity on 1, force of gravity on 2. Notice we've eliminated the human, but they must be there. We've got normal force on both. Force of 1 acting on 2. Force of 2 acting back on 1. The invisible pusher, the invisible mover, force applied. And we declare this to be frictionless, so we don't have any FKs in this situation, okay? It's again like a fictional, non-frictional scenario, okay? All right, so what's the acceleration of the system? Well, we could take the system as a whole. As a whole, and because it moves as a rigid body, we could think of 1 and 2 as being, I don't know, like one super body, right? So we've got mass 1 and mass 2 are going to move together. And of course, that means that if they're moving together, the gravity would be acting on the entire system. Normal will be acting on the entire system. Summatively, and the applied force really is the only external force here because it happens to be frictionless. If there was friction on each individual body would have frictions working to the left in this full body scenario, right? And it looks like, F net y, because the object isn't flying into space or crashing through the Earth, F net y could be assumed to be what? 0, yeah, so 0 newtons in the y direction specifically, okay? But what we want to focus on is the x direction. So a lot of times people will just say, well, I can see by inspection that the y net force is going to be 0. So I'm just going to call F net system. I'll call it F net system, but in my heart, I know that the F net for this system is really just F net x, because F net y I'll just cancel out anyway. And we can say Newton's second law says the mass of the system times the acceleration of the system is going to be equal to the F net. In this case, F net x is really easy to calculate. If there was friction, we could add in the friction, right? Isolate to get a cis all by itself. Sub in our values, F net cis over mass. Be careful, because when we sub in our values, the F net for the system really is just the F applied. And if there was friction, we would have added in FK1 plus FK2. But there's not, so I'm going to get rid of those guys because it's frictionless. And then in the denominator, we would say it's the sum of mass 1 plus mass 2, the system mass. Subbing in our values, we've got the F applied 18.0 newtons plus no friction, divided by mass 1 plus mass 2. I'm going to save myself, I don't know, I'll write it in. 10.0 kilograms plus 5.00 kilograms. I'll put it as a binomial in the denominator. And I think we can just do this as one data entry line in our calculator. What's 18 divided by 15? Nice round number. 1.2? All right. And it's 3 sig figs, right? So we say 1.20 meters per second squared. And only just because I'm concerned about real estate here, because I got another question to solve, can we just declare that that positive value is to the right? Let's just do that all in one line. I know that we don't typically like to do all of it in one line, the rounding and the direction. But the rounding is easy because it is like exactly 1.2. We're just adding the 0 for sig figs, and it's positive, so it's to the right. And then the next question is, what's the net force on each box? Well, to talk about the net force on each box, we should really talk about them as individual boxes. Box 1, we said at the top, this is a rigid system. So the acceleration of the system, whatever that may be, is equal to acceleration 1, and that's equal to acceleration 2. And if I think about the free body diagram for box 1, here I've still got it on screen. This is the free body diagram for box 1. I know that that free body diagram is equal to this diagram, which is to say that all these vectors add up to that picture. Now this is truly the free body diagram. This is a diagram expressing that that would be the sum of all those vectors, right? Notice the y vectors cancel each other out, the x vectors don't cancel each other out. It's kind of lopsided to the right. We know that it's accelerating to the right. That must be the net force diagram for this thing. It's not a true free body diagram. But what we can also say is F net for 1 is equal to mass 1 times acceleration of 1. Because Newton's second law is always true. So we got Newton's second law here for this individual object. And it looks like 10.0 kilograms times 1.20 meters per second squared. So positive, it's to the right. Easy math. I chose nice round numbers on purpose, right? 10 times 1.2, 12.0 newtons to the right. And then I say, hey, what about the other box? As it says on each box. Well, the other box, by the same logic, would have a net force diagram. And a lot of times people don't even bother drawing these net force diagrams, especially if they're simple like this. But the net force diagram would look like this. Notice the y components cancel each other out. All we're left with is the x component, which in this case is force of 1 on 2, according to this picture. But I can make this math statement that Newton's second law is always true. F net for mass 2 is mass 2 times acceleration 2, which, as we said, is the same as the acceleration of the system. So we said it's 5 kilograms times 1.2 and it looks like I've run out of space there, but 5 times 1.2, that's 6, right? 6. So 6.00 newtons to the right. Fantastic. Now here's what I don't want people to do. And it's always a temptation. And people are basically pattern finding machines. We love patterns. In fact, that's really a big part of what science is as a philosophy. It's recognizing patterns in nature and just like going crazy with it, you know? But when I look at this, I say 18 newtons, that's the applied force. 12 plus 6 is 18. What? That's amazing. Pattern. That's a pattern, but it's only going to be true when there's no friction. Only ever true. That's a very special case, okay? So I'm drawing attention to it so that people don't think there's a pattern that is really in reality never going to happen, okay? So don't make that connection. Don't do that. Yeah?
What happens to f of 2 on 1?
Oh, let's talk about that. I love that question. What happens to f of 2 on 1? The question says, part C is about to answer that. So it's like you're reading my mind. Perfect. So what's the action-reaction force between masses 1 and 2? Talk about that. So let's redraw the free body diagram for object 2. We had force of gravity acting down on 1. We have force applied. We have force normal acting up on 1. We have force of 2 acting back on 1. And we know that that picture, because remember, free body diagram pictures are equation-generating machines. We know that that picture is equal to F net for object 1. Because that's the purpose of free body diagrams, is to be equation-generating machines. Now we also kind of know that, because we said it once before, F net y for 1 equals 0 newtons. So we recognize, like implicitly, that we're going to be disregarding the y components here because they're canceling each other out, because situationally this object isn't crashing through the floor. Okay? So the acceleration vertically is 0, so F net y is 0, because I've seen boxes in action. Okay? But then I can say, hey, from this equation generating picture, I make the statement F net 1 equals force of 2 acting on 1 plus F applied. Now it turns out that I've actually already calculated F net 1. So in terms of what do I know this. We just did it in B. What's F applied? Oh, that was given to us at the beginning. It's 18.0 newtons. I know it. And now I have a linear equation where I can calculate force of 2 acting on 1. This is beautiful, right? So I can say, okay, well, no problem. I'm going to isolate force of 2 acting on 1. Force of 2 acting on 1 is going to be F net 1 minus F applied. And now that I've isolated the thing I'm trying to find, I can just start plugging in the values that I already know. Now, if I hadn't previously calculated this, I would put in mass 1 times acceleration 1 minus the F applied. I could do stuff like that. If I hadn't figured out mass 1 times acceleration 1, do you know there are some people that create generalized equations? Mass 1 times, instead of acceleration 1, they say acceleration 1 is the acceleration of the system. So F net cis divided by mass 1 plus mass 2 as a binomial minus F applied, right? And we could really make like a full, like blown out generalized equation for this, where actually this equation would take into account everything that we've done previously on the page, right? And so if we had like a robust enough imagination to think through these things, we could make this final equation and have skipped everything above us on the page. Nice, beautiful, generalized equation, okay? Anyway, if we were to do that, though, we would still end up getting 12 minus 18. And you can try it for yourself, see if you do. And you get negative 6.0 newtons for force of 2 acting on 1s. Now, negative means 6.0 newtons to the left, right? Fine. But then I say, well, wait a minute. That's what I got for force of 2 acting on 1. What about force of 1 acting on 2? If Newton's third law holds up, shouldn't they be equal but opposite? So we can play that game. Let's talk about the free body diagram for object 2. Force of normal acting on 2. This is object 2. Force of gravity acting down on 2. Force of 1 acting over on 2. And by the way, we would get down to the exact same sort of pattern of thinking even if there were frictions. It's just the frictions would make it slightly more complicated, and I want to make sure that we can see how it all works and be okay with it without friction, right? So just simplifying so we can feel good about it. Remember that F net y on 2 is also equal to 0 newtons, so we're going to disregard the verticals there because of the special case scenario that it's not falling through the earth, which isn't very special. It happens all the time that we don't fall through the earth, except there was a sinkhole that I saw in the news that was like 50 meters deep in the news last night, so that's crazy. But I can imagine, it was in a highway too. Like you can imagine you're driving along and a 50-meter deep sinkhole opens out. Like that would shock me. That would leave me in shock. There you go. Civil engineers will never be out of work. All right, so what we end up saying is F net 2, look at that, is equal to force of 1 acting on 2. And by golly, we've already calculated F net 2x. It was just above us on the page right here. It was 6.00 newtons to the right, force of 1 acting on 2. And as I step back and I look at this, I say, yes, equal in magnitude, opposite in directions. Now we happen to, by a fluke of the way sig figs add versus multiply, one's got 3 sig figs, one's got 2, but we still agree with each other. It's still 6 and 6. Well, positive 6 and negative 6 anyway, right? So Newton's third law is still totally a thing.